integral of secant of x dx, which takes a little bit more work, but we're going to be able to make this work with some creativity. I have to say that u equals both secant x plus tangent of x. How would you know to do that? Well, because I do. So this probably wouldn't be a great one to develop on a test, because unless you know the special super duper trick, you'll not get there, but this is one you need to memorize. So that du is equal to secant of x tangent of x plus secant squared of x dx. All. So then I'm going to factor out a secant x. Sorry, my pen stopped behaving. Secant of x, which is tangent of x plus secant of x dx. And then that becomes secant of x u, because that was the beginning, dx. And that du over u now equals secant of x dx. That's what I got. So this becomes du over u, tricky, which becomes ln of u, which becomes ln of secant x plus tangent of x plus c. And that's your integral there. So this is one, unlike tangent, where I feel like tangent kind of flows. Like you could easily, I could ask you what the integral of tangent is without having told you anything, and you should have been able to do that probably on the last test. Perhaps I should have asked that. But nonetheless, the secant with that special substitution that you just kind of had to know to do, that's trickier. So this would be a good one to have memorized, so you have it handy. And we can go over that probably when I return, what formulas need to be done and what formulas don't. Now, in terms of secant and tangent, they're a little bit trickier because in terms of them, the derivative of tangent is secant squared, and the derivative of secant is secant tangent. So it's not quite as pretty as the sine cosine. But there are some relationships that allow us to use similar methods for secant and tangent. They're just not quite as, I can't give you the easy, odd, even delineation that I gave you between sine and cosine. So that's the difference there. So let's do one. Let's try negative pi over 4 2 pi over 4 secant to the fourth of x dx. So again, I don't know how to reduce this. I'm going to have to rely on my identities. So thankfully, I know the integral of secant squared of x, or I should, although that tripped you guys up on your last test quite a bit. So the derivative of tangent is secant squared. The integral of secant squared is therefore tangent. So I'm going to rewrite this as negative pi over 4 to pi over 4. We're going to write this based on our identities as tangent squared of x plus 1, because that's secant squared times secant squared of x dx. In other words, this is not tangent. Well, of course, secant, sorry, it wouldn't erase secant squared of x. That's what this guy is right here. So I basically took secant to the fourth right here and break it into secant squared and secant squared. And then I change that to be tan so I could introduce the tangent because these have a derivative relationship. So now I'm going to make this a little bit easier on myself. This is going to be tangent square root of x secant square root of x plus the integral of secant square root of x. And the whole thing is from negative pi over 4 to pi over 4. Just changing the notation so it's easier on me, that's all. This guy is tangent of x. That's easy. This guy is not so easy, but we can use a u substitution. So this is going to be u equals tangent of x. And I picked that because du equals secant square root of x dx. So I lost my dx up there. So dx secant squared become du, which makes this u squared, and the integral of u squared is u cubed 1/3. So this is 1/3 u cubed, which is going to be 1/3 tangent to the third of x, plus tangent of x. And no plus c because we're going to deal with bounds. Do an arrow because those aren't equal. So at pi over 4, we've got a 1 relationship. Depending on where we are, which quadrant, we might have a negative 1. It's going to be one of the two. So at negative pi over 4, we're in quadrant 4. Pi over 4, we're in quadrant 1. So quadrant 1, it's going to be a positive over positive. In quadrant 2, it's going to be a negative over a positive. Negative y's, positive x's. So let's put this out there. This is going to be 1/3 1 cubed plus 1 minus 1/3 negative 1 cubed minus 1. So 1/3 plus 3/3, changing it to thirds, plus, because that negative 1 cubed mixed with that is going to make positive 1/3 plus 3/3, and that's going to be 8/3. Okay, so there are some reduction formulas for secant and tangent, and they're on, I have it written in my notes on page 438. You're not required to memorize the secant tangent reduction formulas. You should know the sine and cosine ones. You should be able to do a secant tangent problem that is doable using substitution and not necessarily one of the reduction formulas. However, with the sine and cosine problems, I should be able to throw any power, and you should know to attack it. You should know that if it's odd, at least one is odd, then you do a substitution. You should know that if one is even, or if both are even, then you need to how to divide them up and to go ahead and use a reduction formula. And then if you have just a single cosine or sine to some power, you can either use the reduction formula or you can break it up and approach it from that nature. So you have some options there for sine and cosine, and I expect you to understand those options. Tangent and secant, maybe not so much. If I throw a tangent or secant problem on there with a higher power that you need to use a reduction formula for, I will provide the reduction formula, but I'm telling you I probably won't do that because you guys are smart guys and girls, and you can copy a formula down off of a sheet. I think that I would either stick to tangent, secant ones that are doable without a reduction formula, or the sine cosine, which I might ask the reduction formula, or any number of other exciting things to get that to work. Okay? And on that note of what you're required to know, what you're not required to know, on page 438, lost my stylus, on page 438, There is an extremely long list of formulas. In fact, the whole chapter has a bunch of formulas. And I can't expect you to memorize all of them. So I expect you to know number 11, formula 11 and 12, which are the sine squared and cosine squared. I expect you to know the reduction formula for sine, which is 13, and the reduction formula for cosine, which is 14. I expect you to know those. You can derive 15 and 16 on your own, no problem, with the methods that we've discussed. You can just go ahead and manipulate them. There's no reason to memorize those. I expect you to know 17 and 18. Because that, 17, nope, not 18. I expect you to know 17, because 17 is the integral of tangent, and I expect you to know the integral of secant, so 21. I expect you to know the integral of cosecant, 23. And I expect you to know the integral of cotangent, so that is, it looks like 20. Nope, 19. And then on the bottom, there's what to do with the sine of mx and sine of nx. And those formulas are really problematic. Those are one of those things that if for some reason you're required to do it in a homework assignment or whatever, you can look up that formula that will allow you to shift the constant coefficient to whatever your x is. So you do not need to memorize those, but I want you to know about 25 through 27 being there. And these are if you're doing an integral of sine nx cosine mx, and how to rewrite the problem to deal with the different coefficients. If it's the same coefficient, like u is 2x, then that's no problem because you can just sub in, but you can't sub in there. So that's more problematic. And they give you these nice formulas, and it has to do with essentially using those identities where you can go sine of m plus n is whatever. And they're nice to know, but you're not going to be required to know them for a test. I won't give you any questions that has that in there. Okay? Okay, homework. Fun. 7.3. 3, 5, 9, 11, 13, 21, 23, 25, 31, 39, 43, 47, 49, 57. Have fun.